we're going to talk about Reactor. But first we're going to talk about me, because that's important. So I'm James, and I live in a tiny rural town, about an hour from Wellington, New Zealand. It's about a population of about 3,000 people. Given the small population and that most of the local economy is dairy farming, I feel confident suggesting I might be the best Elixir programmer in town. But I am also probably the only one. I've been writing and releasing Elixir into production and into other people's dependencies for about a decade. I'm a member of the Ash Framework core team, and I'm responsible for a bunch of Ash extensions like Ash Authentication. And yes, you did see one of my CVEs on the screen just before. Ash Ops and Ash Rate Limiter, just to name a few. In my spare time, I really love to build things. So yeah, I build a lot of software, but I've also been known to make furniture, robots, and comically large quadcopters. I work for Alembic, who give me the time and the space to imagine new ways of solving problems, and I'm extremely grateful for that. And I love my dogs, my kids, my stepkid, and my wonderful partner who is here in Berlin with me. Without all of these people supporting me, I'd never be able to do the awesome work that I get to do. So let's talk about Reactor. Reactor is a graph-based concurrent Saga runner. That's a lot of words. We'll go through it. I wrote it and now maintain it with the help of the Ash core team. Thank you. But I don't need Ash. You don't need Ash to use it. They just work well together. But Reactor does stand on its own. Reactor's Saga system is designed to let you have transaction-like semantics across system boundaries by allowing tasks to both compensate for any failures they may have or undo any work they've done. It automatically runs tasks concurrently whenever possible, and reactors can be built dynamically with a builder API, so programmatically, or using a Spark-based DSL, much like that used in Ash. All the examples in this talk use the DSL, but know that everything you see can also be built programmatically with the builder, and in fact, everything that you type into the DSL runs through the builder to turn into a struct. So the key parts of Reactor is the concept of steps. We define a workflow as a list of named steps, and then we describe the dependencies between them as arguments, which refer to other step results, inputs, or even static values. Reactor's builder creates a graph of all this information, confirms that it's not cyclic, so no steps accidentally depend on themselves somehow, and then returns a struct which contains all the information needed to execute the reactor. And this is a very contrived, very basic reactor. You would not do this. You would use Ash Authentication. Please use Ash Authentication. The DSL is designed to help you describe the problem that you're solving at kind of the same level of abstraction, and the goal is to express your problem without you not worrying about the how so much as the expression of the links between the parts. So let's go through it and talk about what you're looking at. Most reactors need inputs. You can think of an input as an argument to the reactor itself. So when you call reactor.run my reactor, you need to provide those arguments, and they're named. And it will not start unless you provide them all. You can just provide nils, obviously, but you need to provide them. So this example needs, obviously, an email address and a password. The first step on our list is called validate email. So each step defines what it needs to run in terms of arguments. So this one says, hey, I need an argument called email, and I want to take it from the email input to the reactor. So Reactor looks at this and it goes, oh, sweet. You don't actually have any dependencies because that one's already supplied. So it knows it can run it immediately. it checks the validate email module and it goes, oh, okay, as long as it implements the reactor.step behavior, we're good. So the dependency is explicit, and this is where the power of the graph comes in. The other thing to point out about steps is that they're asynchronous by default. You can say, hey, this step has to run synchronously, or this group of steps needs to run synchronously, or this entire reactor needs to run synchronously, but by default, everything runs async. So the second step in our list is a hash password step, which takes a single argument. This also comes from an input, so Reactor knows, sweet, you're up first. And the last step is our create user step. It takes two arguments, which are the results of the previous two steps, and obviously creates a user somehow. And then we say, when you're done, I want the result, whatever the result of the create user step was, I want that as the result of the reactor. Importantly, ordering is completely arbitrary, has no impact on the way it's executed. In fact, I would say the ordering is non-deterministic because it uses the reactor to figure out uses the graph to figure out the dependencies. So that means that you express the problem in whatever order works for your brain, not in whatever order you think reactor needs it in. So when we run the reactor goes, oh sweet, these guys have no dependencies. It fires up 2 tasks and runs those steps inside them. Waits for those tasks to complete, and then it passes the results into the create user step, which it spins up in a new task, waits for it to complete, and then returns the result. So that's cool. That's cool when everything goes well, but as we all know, not everything goes well. So we've covered the happy path, but what happens if something goes wrong? And this is where what we call sagas come in. Steps, the reactor.step behavior lets you define callbacks to compensate for your own failure. So if you do something wrong, you can fix it, hopefully. Or you can undo your work if some other step failed and now we're trying to undo the work we've done before. Without these, you don't have to define these callbacks, and without them, Reactor just collects up any errors and goes as far as it can, and then reports back like a normal function, I guess. Now, this is what our create user step could look like if we were, for example, creating the user in some random identity provider on the internet, like Auth0 or something like that. So if the run function errors, Reactor captures it and it goes, oh, you've got a compensate callback. Cool. I'll call it and you'll get the error. And in this case, we can say, oh, this was a timeout, like a network timeout. Just try it again. And Reactor will go, okay, sweet. And it will put the step back into the graph ready to be run the next time we're looking for steps to run. If the step can't compensate, like in this case, the pattern didn't match, so it moves on to the next one. Well, we can't do anything about that. We'll just return the error, and Reactor goes, okay, cool, we've had a step failure. I'm going to switch to undo mode and go back through all the things that have been done before, check if they're undoable, and undo them. And so we also define an undo optional callback, and in this case it's saying, hey, delete the user, because something after us failed. For example, say we were going to send them a welcome email or a magic linking email, but we couldn't because there was another failure downstream. Then we actually want to delete that user and start from a clean slate, much like a transaction in the database. Because of Spark being as awesome as it is, we can extend Reactor, just like we can extend an Ash resource. And there's a bunch of extensions already. And these extensions can not just add new step type modules, but they can add new DSL dynamically so you can express things at a similar level of abstraction. So this is an updated version of what it might look like if we used the Reactor rec extension. We we use the built-in collect step, which is a wrapper for a step called reactor.step.return all arguments, which does exactly what it sounds like. It basically just says I get a map of arguments and I return a map of my arguments. And we use that to build our JSON payload. And then we use rec post, which comes from the rec extension and allows us to call that step. But it also, because it defines the DSL, it can define some constraints, and we can do some compile time checking that some of the some of the arguments are being called the right way or have the right values. So yeah, there's a handful of extensions already. Reactor rec we saw, which lets you do HTTP requests. Reactor file, which lets you work with files on the file system. It basically implements everything in Elixir's file and path modules, but most of them are undoable. So like if you delete a file and you want it to be undoable, it'll move it to a temporary directory and then delete it when the reactor actually completes, things like that. I also have a bunch of ideas for new ones, but I want to hear about your use cases, so tell me afterwards if there's extensions you would like to see in the Reactor ecosystem. So we're here to talk about under the hood. We've talked about what Reactor is, but we want to talk about how it works. Running Reactor isn't just about running the steps in the order. We've got concurrent tasks, we've got dynamic graphs, which means some steps can return results and more steps. And we've got steps that can fail or need to undo their work, as well as nested reactors, so reactors running inside other reactors, in loops and things like that. So it's easy to see how this could devolve into a mess of really complicated state machines, or, who knows, callback mess, lots of conditionals. So I spent quite a lot of time thinking about this problem, and really what I want to talk about is my favorite loop. And I think the best loop in my career that I've ever written. So this is what this talk is about. Cool. So the main core of Reactor is a loop, and it continuously loops until there's no work left to do. And it goes through a bunch of stages, like checking for timeouts, checking for finished tasks, checking for lots of, like 9 of them. There are 9 stages that we need to go through. But the cool thing is every one of them can return one of 4 things. We return continue, which means I didn't do anything, move on to the next stage in the process. Recurse, which means start over from the beginning. Halt, which means pause execution and return a partial result, so reactors can pause. And undo, which means there was an error, you need to change tax and start undoing work. Now, out of the 9, there are 3 different stages specifically for running steps, and I wanted to focus on them first. The first is try and start as many asynchronous steps as you can. Try and run a synchronous step, and then run any step, I don't care. And the last one seems weird, but we're going to talk about why. There's a subtle deadlock problem. Imagine you've got a reactor that's allowed 16 tasks, 16 concurrent jobs, and it's happily churning through work. 15 steps are already running, taking up tasks. Then it hits a compose step that needs to run another reactor. So we take one of the limited slots for this compose, and now we start another reactor, and it doesn't have any concurrency left to make progress. And this is especially bad if all your 16 slots are used by reactors trying to run more steps, which happens. So the reactor grabs the last available slot to start the inner reactor, but now the inner reactor needs to run its own steps and there aren't any left. So we're going to talk quickly about how we manage concurrency and limiting it, because it's a little more complicated than usual. So we're going on a side quest. We have a thing called the concurrency tracker, and without them, every reactor in the system could run tasks up to its concurrency limit, which is originally how it worked and caused me many headaches. For example, if you're running the same reactor twice with 2 inputs, and say your concurrency limit is 16, then now you've got 32 tasks all trying to make progress. And if they're all running reactors, now you've got an exponential problem of tasks all trying to make progress. So we came up with the idea of concurrency to pools. And when you start a reactor, you can explicitly pass in a concurrency pool, or it will create one if you don't, based on the limit, and the limit is, by default, is number of schedulers online times 2. But this unlocks a cool feature. It means that nested reactors don't have to be any kind of special, they don't have any special call. We just say, what's my concurrent pool reference, pass it into the child reactor when we start it. So they don't need their own rules, they don't need any special code, it just happens to work. So when we're asked to allocate a pool of a certain size, we insert a row in an ETS table, and that row contains the reference, which is kind of our key, the concurrency limit, the concurrency available, which obviously is the limit when we start, and the PID of the caller, which we then monitor in case it dies without telling us it needs to release its pool, and we can delete the row. So when a reactor asks for some slots, it says we use select replace, and we call it repeatedly, saying, can you reduce the available concurrency by 1? And as long as that happens, and there's always at least 1 in the table, then we're good. This horrible chunk of tuples and atoms and lists is what's called a match spec, and many people, I see people nodding. I love them, I think they're fabulous, but also you don't have to make them yourself. You can write an anonymous function and you can ask the ets module to spit out a match spec that matches. So there's a pro tip for you. So because it's looping and getting 1 at a time, you can say, can I have 16 slots? And the concurrency tracker will reduce until it gets, I couldn't get you another one. I didn't update any rows, so you've got 4, for example, or you've got none. But also because it's looping and doing 1 at a time, if multiple reactors are asking at the same time, they're synchronized because select replace is atomic. So it means that the first one to ask doesn't get 16 and the second one gets 0. They kind of interleave their requests. So this is a cool solution, but it does lead to a deadlock problem. So how do we fix that? So when our inner reactor tries to run, we say, can I get a slot to run some async tasks? No, there are none left. Are there any synchronous steps that I can run? In our example, there aren't any synchronous steps, but there also might not be any left. Like we might have done them all already. So on the third attempt, we go, forget it. I nearly said another F word, sorry. Forget it. I'll just run an async step right here synchronously, because when you think about it, I'm already running in a task from another reactor, so I'm implicitly asynchronous. So the inner reactor is able to make progress, and who knows, next time through the loop it might even get some slots. So we've seen how the 3-attempt pattern prevents these deadlocks, but that's one part of a larger orchestration. And remember I said every stage can return one of 4 things. Continue to the next stage, recurse with a new state, halt execution, or trigger and undo. And this consistent pattern is what makes the whole thing tractable for our small human brains. It's where Elixir's with statement is perfect. It lets us chain these stages together and for the happy path, and then anything else is handled cleanly with the else clauses, which means that we don't have big nested loops or functions or state machines or control flow. So this is what it looks like. This is the entire orchestration engine of the reactor in 17 lines of all reactors. For non-elixirists, with effectively flattens case statements, as long as each expression on the right matches with the expression on the left, then we continue down the list of clauses. And when we get to the end, we run whatever's in the do block. And if it doesn't match, then it has to match one of the else clauses. So it's like, yeah, it's squashing. You can imagine a deeply nested case statement goes to the right a long way, and instead we avoid it by using with. But look at how it reads. It's like a checklist. It says, have we timed out? No. Are there any new steps? Are there any completed tasks? Are there any steps to start? So this is my favorite loop. It isn't clever. I'd say it's graceful. It's dumb, and it solves a complex problem. So each stage does one thing, returns what we expect, and the whole thing kind of just works. The complexity is in the problem and not in the solution. And that's what makes me proud of this. When another engineer looks at the code and they go, oh, is that it? I'm like, oh yeah, that's it. That's exactly the reaction I want. And just as a little side quest, in September I got home from Goatmire, and I was inspired to add Reactor features based on the conversations I had, and one of them was like, why don't we do back-offs? And I was like, yeah, you're right, I was just lazy. We should totally have back-offs in a Reactor. And the idea is that if a step fails, you can tell it how long to wait before retrying. Most systems, this would be a big refactor, and it would probably involve some timers and things like that, which is a way to do it. But in Reactor, it was easy. I found the spot in this loop where we'd done everything else we could usefully do, and I was like, okay, go check some timeouts. And this is what it looks like. When a step needs to back off, we create a new back off vertex in the graph, and we make the step depend on it. The back off just contains a millisecond, monotonic time of when the back off expires, and means the step literally can't run because it has a dependency. So this function runs when the loop eventually gets down there and deletes those vertices if they've expired, and then suddenly they are available to be scheduled again. So this is what I mean about boring code solving hard problems. So what have we learnt? Graphs are cool. They allow us to do things like automatic concurrency and dependencies, so we don't have to think about the order things happen, and it helps us think in a similar level of abstraction. Saga pattern, awesome, works really well, so you can have transaction-like behavior across boundaries without distributed transactions or anything like that. Third, the deadlock example is a real bug that we hit early on. It was driving me mad. And the solution wasn't to add deadlock detection or any timeouts or anything like that. It was to order the operations thoughtfully. And I can't take credit. My collaborator, Zach, had already solved a similar problem inside Ash, and so he gave me some pointers. But finally, there's a bit I really want you to take away is that the best code is boring code. And that's why I want you to mentally substitute boring for graceful. It's easy to make complicated code to solve complicated problems, but especially now that we have AI coding assistants, it's a lot harder to find a graceful solution. It took me weeks to figure out that loop structure, but now it looks super obvious. That's it. So Reactor is open source, it's in production, it's ready to use today, works standalone or as part of Ash, and come and talk to me about it afterwards if you're interested. And I have to say, thanks to Alembic for getting me here. If you want to talk to someone about your next Elixir project, come and talk to us.
Thank you so much, James.
Very good.